Hello everyone, my name is Wenliang Liu. I'm a PhD student in Boston University. Today I will talk about my work in recurrent neural network controllers for techno-temporal logic specifications subject to safety constraints. First, let me introduce our motivation for this work. Classic control studies simple specifications such as stability and set invariance. On the other hand, temporal logics are very expressive. They can express much more than stability and set invariance, and they are similar to natural languages. Hence, temporal logics have been used to formulate specifications for cyber-physical systems. In this paper, we focused on signal-temporal logic, or STL. Here's an example of an STL formula, which can be interpreted into English as for all temps in 0 to 7, eventually visit region A every 4 steps, and eventually visit region B for every 4 steps. The regions can be seen in this figure. This specification requires the robot to move back and forth between these two regions within the given time interval. This is a very rich specification. Hence, we want to solve the problem of control synthesis from STL specifications. That is, given a specification in the form of STL formula, we want to find a controller which can steer the system to satisfy this specification. Another property of STL is that it has the quantitative semantics, also known as robustness, which measures how strongly the specification is satisfied. Take advantage of the robustness, we can formulate the control synthesis problem as an optimization problem. That is, we maximize the robustness and minimize the cost function. Some methods have been proposed to solve this problem. Some of them use Smith integer programming in the model predictive control manner, and some of them smoothen the robustness and use gradient-based optimization methods. Both of these methods are computationally expensive, especially for high-dimensional systems and long planning horizon, which prevents real-time implementation. To solve this, we can use learning-based methods. Feed-forward neural network controllers for satisfying STL specifications have been proposed. However, FN controllers are memoryless, but STL is history-dependent. Let's look at this example again. Suppose that the robot is at the center of these two regions. Given only the current state, the robot cannot decide which region it should go. It needs to know which region it has just visited so it can go to the other one. So a memoryless controller cannot satisfy such specifications. Q-learning-based methods are proposed to solve this history-dependent problem by restricting the STL formula into STL fragments. Well, for linear temporal logic, it can be translated into automaton, which can capture the history, but STL cannot be translated into automaton. In this work, we proposed a recurrent neural network controller, where the input is the current state and the output is a proper control that steers the system to satisfy the given specification. Since Rn has the memory of history, it can in general satisfy full STL specifications. To train the Rn controller, we first solve the control synthesis problem using the aforementioned gradient-based method for many temps and generate a dataset. This is called the direct solution. And then we train the Rn controller on this dataset. Although the direct solution costs a lot of computation, it is implemented offline. After training, the Rn controller can be used for online control, which is very fast and enables real-time implementation. On the other hand, we decompose the safety constraints from the specification and use control barrier function to guarantee safety. Look at this example. These red circles are some random obstacles. Suppose that we have a reference control which is from either the direct solution or the Rn controller. We use CBF to adjust the reference control to get a safe control which avoids the collision with the obstacle. Doing so has two advantages. First, we can handle safety constraints which are unknown during training. Second, we can guarantee safety independent of the performance of the RNN. These are because we use the CBF after the RNN. Before formulating our problem, let's look at some notation and preliminaries. We consider a discrete time dynamical system sigma where Q is the system state and U is the control input. We use this compact notation for a sequence of controls and sequence of system states steered by these controls. Now let's look at definition of STL. STL is defined over signals. Here a signal is the sequence of system states. STL specifies temporal requirements of signals over time. It has the syntax like this. We can also define other Boolean and temporal operators. In this paper, we use the AGM robustness, which is denoted by eta. Eta is a sound score, which means that if it is greater than 0, the formula is satisfied. Otherwise, the formula is violated. The time horizon of the STL is the minimum trajectory length required to decide the satisfiability of an STL formula. Now let's look at control barrier functions. A function B is the discrete time exponential control barrier function for system sigma if there exists alpha and for each qk there exists uk such that these inequalities are satisfied. The set C, which is the upper level set of B, is forward invariant for system sigma if there exists a control barrier function B, where invariance means that all trajectories remain in C for all times if they originate in C. This property of invariance is often referred to as safety. Now we can state our problem. Given system dynamics, cost function, STL formula, initial state, and safety requirement, we want to find a control sequence that maximizes the STL robustness as well as minimizing the cost function and satisfying the safety requirements. Instead of synthesizing the control sequence in one shot, which gives us an open-loop controller, we decompose it into two subproblems, problem 1 and 2. We solve them at each time step, and this gives us a feedback controller. By solving problem 1, we can get a reference control that provides a direction for the satisfaction of the specification. Then by solving problem 2, we adjust the reference control to get a safe control. We repeat this for many times and generate a dataset which consists of satisfying trajectories. Then we train our controller on these datasets. Now let's formulate problem 1 and 2. In problem 1, at each time step, given the history trajectory, which is this blue trajectory in this figure, we want to maximize the robustness and minimize the cost function over the future control sequence, which will generate the red trajectory. Then we only pick up the first control in the sequence, which is called the reference control. Then in problem 2, we adjust the reference control in a minimal way such that the CBF constraints are satisfied. Both of problem 1 and 2 are solved using SQP. Now let's look at the RN controller. At each time step, the input of the RN is the current state, and the output is the prediction for the reference control. By passing the hidden state HK, RN can capture the history inputs. To train the RN, we minimize the difference between the output of the RN and the reference control. Note that the RN controller is trained on the reference control instead of the safe control. This is because we solve problem 2 after the RN controller to make its output safe. This makes the the controller more flexible because it can deal with unknown safety constraints during training. The reason why we also solve problem 2 when generating dataset is because we want to explore more states. Finally, let's look at 2 case studies. In the first one, the specification requires the robot to eventually visit region A or region B in the first 10 steps, and eventually visit region C in the second 10 steps, and always avoid the rectangle obstacle. There are some random circular obstacles in the environment. Avoiding them is the safety constraints. Here are some trajectories generated by our RNN CBF framework. We can see that they satisfy the specification and avoid the obstacle successfully. The RNN solution is much faster than the direct solution, which enables real-time control. Second case study is the aforementioned example. We can see that by using our RNN controller, the robot can successfully move back and forth between the 2 regions, which proves that the RNN controller can capture history. For conclusion, we proposed an RNN framework for control synthesis from STL specifications. We used the CBF to guarantee safety. Our RNN controller can be implemented in real time and achieve high success rate. Future works include considering unknown system dynamics and incorporating with reinforcement learning. Thanks for listening.